Hi, welcome to the week 2 of artificial intelligence lectures. And today we are going to finally start talking about AI models. And all right, let's start with linear models. So, last week I gave a brief introduction to different types of models we'll be talking about, and linear models is the first one, or the first group of models that we are going to have a look at. So these belong to uh, the branch or the umbrella of supervised learning models, and we talked last week how supervised models mean we tell the machine that this is how something should be, and then the machine learns to recognize that particular pattern. So let's see how we do this supervised learning in linear models. So linear models could be in many forms. So here we have a linear regression model. So basically we have an independent variable and a dependent variable, and we are trying to figure out the relationship between the independent variable and the dependent variable, or the between the predictors and the response variables through a linear function. So you can see that here we have tried to come up with a trend line which matches our observations. So that is a linear model. It's a linear regression model. So regression is where we measure the relationship between the independent variable and the dependent variable. And then we have another linear model here, which is a linear classifier. So this is a regression model here, linear regression, and then here we have a linear classifier. Here what we are trying to do is we are trying to find a line to segment our observations into two classes. So we have these solids on one side and the whites on the other side, and imagine we have a new observation here, and we have a fairly good idea where that would belong to. Well, we'll have a fairly good idea if we are using this line H2 as our line, right? So there's other lines displayed here, but you get the general idea. So here our task is classifying, while in the previous one our task was finding a continuous variable, which is the linear regression. And we have this other thing here as well. Again, it's a regression model, but this is a polynomial regression, which is also a linear model. So when we say linear models, we don't have to think that they are going to be a straight line. It could be a polynomial relationship as well, right? So we will be talking about a couple of these linear models. Specifically, we'll be focusing on linear regression models in the this week and the next week as well, probably. We won't go much into linear classifiers, but maybe towards the middle of the semester we'll be talking a little bit about classifiers, and then we'll revisit the concept of the linear classifier. And the polynomial regression, it's not for the scope of this module, but it's always a good idea to know what is out there. So there you go, the polynomial binomial regression. So okay, let's go and see like where we can't really use linear models. So this is a very famous construct called the Enscombes construct, where they show that linear models don't always work. So this construct, Enscombes construct, or Enscombes Quartet, actually. So Enscombes Quartet is these 4 datasets that have like very identical statistics when we compare them. So they have the same mean, same variance, and very close correlations, and they have the same linear regression line, as you can see. But you can see that it works well for this, we can say. Works all right for these observations here. It doesn't work really well with this. Like maybe this is an outlier, right? But like look at these two. Like it does not capture the pattern at all. So this is why we would say that linear models does not work for all the data sets out there. You could potentially build a linear model, but doesn't mean that you should be using one. So you will see that when we actually build models for practical use cases, we will be visualizing the data first to see how, like, does this data set follow a linear pattern. So it's always a good idea not to just look at statistics, but to look at a visualization of your data, right? So that you will not fall into any of these pitfalls. So you can read more about Enscombes Quartet. It's Quartet, not construct, on Wikipedia, or you can just Google about it if you want to learn more. But this is a very good example on why linear models don't always work. So okay, we are going into regression. So linear regression, this is like one of the topics we will be talking about quite a lot in this week and the coming weeks. So first, let us clarify what regression is. So regression is a measure of relationship between the predictors and the response variable, or a measure of relationship between the independent variable and the dependent variable. So we are interested in seeing how the dependent variable affects the independent variable. Oh, sorry, the other way around, like how the independent variable affects the dependent variable. So say something like the number of hours you have worked. So number of hours worked, and you have your salary. So we would assume that something like this would follow a linear model. So the more you work, more your salary would be. So not really true, but like let's think that this is for the same job, right? So we can say that okay, there is a linear relationship. So what we are interested in finding is basically the properties of this line, right? So when we have a line like this, we are interested in finding m, and see if we are looking for a line like y equals mx plus c. So these are the parameters we would like to estimate. So in order to find a linear regression, we do a parameter estimation, right? So we can generalize this by saying, okay, for a set of y, we can say that x times w plus b. This is what we are looking for, because we are looking at this as a model, not as a 2D line, right? So here w are the weights and b is the bias. So this is a generalized linear model. So a generalized linear model that we can use for linear regression. So let's see that now that we know what linear regression is and where not to use it, and how we are going to use it. Like, we have to know what are the assumptions involved with linear regression. So let me go here. Okay. So obviously we assume that our response variable y would be a linear combination of the parameters. So if our response variable y does not look like it's a linear combination of the parameters, so let's say let's take a simple scenario where we have our x, just one parameter and just one response, and we see something like this, right? So we see this and we immediately know that this is not a linear combination of the parameters. So this is a big no-no for linear regression. So if we can see a data set where the data more or less follow a linear relationship, and we are like, oh yeah, sounds good, we can make a linear model out of this, right? So that is the primary assumption, I would say. And then we have the second assumption, that predictors are not random variables. We assume that they are fixed values. So x values, we assume that they are fixed, they are not random. So yeah, I won't go too much into the mathematics there, but this describes that if our predictors are also random, then we have to know how they vary, right? So they are fixed, just the dependent variable or the response variable are changing, and that is according to this relationship we are interested in finding out. And our next assumption is that the variance is constant. So for example, let's say we have a linear model and we have assumption our data points around this line. So this is the variance, right? So the distance from our line to the actual value. So we assume that these are constant and not proportionate to the actual y value. So because in most cases we would assume that if we are predicting something small, we'll have a smaller error, but if you are predicting something bigger, we'll have a bigger error. So we assume that that's not the case. I'm gonna clear this because this might get confusing for you guys later when I give you the slides. So let's get rid of that. And then we assume that errors are independent. So errors of different observations are independent. So we have this error and we have this error, and these are independent of each other. So we assume that there's no relationship between this epsilon 1 and epsilon 2. And if there was a relationship, then of course our predictions would get more complicated. So these are like some simple assumptions that are involved in using a linear regressor. But there could be like some other assumptions. For now, like we will just keep these in mind. Okay, so let's move ahead, and we are now looking at some variations of linear regression. So we'll be looking specifically at a logistic regression as well, but I will describe what these are, just so that you can have some knowledge in other forms of regression. So logistic regression is just linear regression but sent through a logistics function. So a logistics function is something like this, right? So this is helpful when we are classifying things into classes. So imagine we have some observations here and some here, and if we write a linear regressor, so it could go like this. And so sorry, my lines are not the best. Let me. Okay, so this is our logistic function, and this line. So a logistic function is used when we do logistic regression. So we will just send our regression value through a logistic function to get our estimate. And as I mentioned earlier, it is useful specifically for cases where we are interested in classifying using regression, because when we are not interested in a continuous value, but when we are looking at these what do you call it, like this binary kind of value, so where it's like either 0 or 1, using a logistic function will make our lives so much easier. All right, so that is logistic regression, but don't worry, this is just a very basic explanation. We will be looking at that in much more detail probably next week, or could be this week as well. Depends on how I go with these lectures. I'm trying to keep them each one really small, but let's see. And then we have multivariate linear regression. So multivariate is where we have multiple dependent variables that we are predicting, or multiple response variables. So that is multivariate linear regression. And then we have multiple linear regression, where we have multiple predictors. So it's like sort of the flip side of each other. And then we have polynomial regression, which we talked about earlier, which is a special case of multiple linear regression, where like we can describe a linear regression through a polynomial function. Okay, so that's it for different variations of linear regression. And then now let's look at some applications of linear regression. So we already sort of talk about finding trend lines of data, and I guess we can now add another one, which is sorry, I'm trying to write here, which is classifying things. As a classifier, we'll say as a classifier. Maybe I need to make this a bit bigger. Let me see. Okay, that looks good. And what else? So maybe I'll stick to writing. That seems to be the easier thing to do. So okay, so I mentioned that finding trend lines and as a classifier, and then maybe let's look at some fields where we can use this. This is like linear regression is used in epidemiology quite a lot, epidemiology, and finance and economics, because we are in finance and economics or epidemiology, we are interested in finding out relationships between our dependent variable and the independent between the independent variable and the dependent variables, and I guess these sort of fall under the finding trend lines territory. And in agriculture, so something quite famous is that the output of agriculture is dependent on the amount of land and the amount of fertilizer. So for example, like this is a very simple linear model, which is I think this is the basic this is a very basic economic concept in agriculture. If you use more land, you will get more output. If you use more fertilizer, you will get more output. And if you use less fertilizer but the same amount of land, what happens? Our output goes down. So not to get political, but we experienced this recently in Sri Lanka, where we reduced the amount of fertilizer we use in our agriculture, but basically is the same land and expected the same output. But what happens? It goes down, right? So this is expected if you had an idea about a simple linear relationship between these variables. So I might just remove this to give you the slides later. And what else we can use? We have like so many fields where like something like this, like a generalized linear models are used, and in association, linear regression is used to describe variables. So ecology is another aspect. In ecology, most of ecological relationships are described as sometimes multivariate linear models or sometimes multiple linear regression problems. So yeah, there's a lot of applications to this, and we will be looking at some of these applications in the next lectures. So before we stop for today, we'll look at these linear classifiers as well. So The idea of the linear classifier is to find the best line that describes the separation of the two classes. So here we have three lines. So H1 seems to be a good classifier, and this is H2, seems to be a good classifier. Then we have H1, again not too bad, but we have H3, this is really bad. So let's say, like, if we do introduce a new data point, let's say we introduce a new data point here, so that makes H1 to be a bad one, but H2 still does it well. But what if we introduced our new data point here? Then H1 is the better one, and H2 the not so good classifier. So how do we know, without these new introductions, which one is the best? So what we do here is we measure the distance from our line to our observations, and we get the summation of all our distances, and that will give us a metric. Not the summation, excuse me, we take the variation of the distances, and higher the variation, the worse the model. And of course, if all of these are at a similar distance from our trend line, okay, that is a better model. So that's how we know that H2 is the better model. So because the distance from H2 to these observations all are quite the same, right? But with H1 you can see that the distances are quite far off for some and quite close to others. So it's not the best classifier line, while H2 is a better classifier line. So this is another linear model which we are not going to talk too much about at this point. And yeah, that's what we talked about today. We talked about different kinds of linear models, and we talked that these are supervised models, and we talked about different types of linear models, linear regression and linear classifiers. Then under linear regression we talked about logistic regression, multivariate regression, multiple linear regression, polynomial regression, and then we talk about where to use these, where not to use these, what are some simple applications. And in the next lecture we'll be looking at an analytical solution to a linear model, and then in this lecture we'll be doing some coding exercises as well. So I would like you guys to install a general Python installation with TensorFlow Keras is what I'm going to use, and scientific calculation libraries such as scikit-learn, NumPy, and yeah, like you can install the libraries as you go ahead, but yeah, like please do have a Python installation ready so that we can so that you can follow me in the next lecture. And for Python, there are 3 options. You can either use PyCharm. So these are 3 options that I suggest. There are multiple options. PyCharm is a good way to go, and then you can have an Anaconda installation. That's very easy to deal with respect to packages and stuff. And the other option is to use Google Colab. So this has everything installed in already. So yeah, you just need to have a Google account, and you can use Google Colab. I think this would be the easiest option, but it won't be on your computers. So some people might like to have their codes on their computer, and they can use either PyCharm or Anaconda. I don't really mind, but yeah, please do have that ready, because we'll be coding in in all the other weeks in this semester, right? So okay, now this lecture is it's past half an hour, so I will stop for now and see you in the next lecture with the analytical solution to a linear model.